I didn't do it.
I got 20. Okay. That's a lot better. I'm not sure what happened. And I just got to jiggle the cable a little bit. Okay. Sorry, we had a few technical difficulties on this end. Can someone say something who is on Zoom?
Yeah, we can hear you.
Hello.
Okay, good. Yeah, I'm not sure what happened. I tried to log in and somehow I didn't get the class or something. I don't know. It's kind of a mystery to me. Okay, so today what we're going to do is we are going to review. So this is review part 1. Okay. So what I'll do is I'll go over some of the material on the midterm this class, and then on Monday I'll go over the rest of the material. So let me remind you the sections for the midterm. So midterm 1 will cover sections 1.1 to 1.9. All right. Now I checked, and you should have you should have received all your homework up to homework 3 in your OneNote. So those should all be graded. The grader is working on homework 4 now, which actually includes 1.9. I've tried to encourage her to have it done sometime either Monday or Tuesday. So hopefully that'll be actually graded by then. But hopefully you have a copy of that so you can just study for the midterm from 1.9. Okay, are there any questions on this? No. Okay, so the first point I want to make is there are several definitions that you should just memorize by heart. Okay. So let me just recall some definitions. Let me just say this. So these are definitions to know. Okay, so one is the definition of linear independence. Okay, so we'll actually go over this later on, but I just want to kind of give you a list of things that you should kind of check off and make sure that you know the definitions of. You should know what it means for vector to span. So if I ask you, like, what does it mean for a vector to be in the span of other vectors, you should go write down a definition. Okay. You should know the definition of linear combination. Okay, you should know what it means to be a linear combination of something. And then the other definition I want you to make sure you have down is the definition of linear transformation. All right, so we'll actually go over some of these during the review. I just want to put up front what definitions you definitely need to know. Okay. Now, not only should you know what the definitions are, but you should know how to apply the definitions too. So you should know how to apply the definitions. Okay. All right, any questions? All right. So now let me move on to some of the topics. Okay, so the first topic we started out with was a linear system of equations. All right, so at the beginning of the semester, we looked at linear systems where there were m equations and there were n unknowns. And what we saw was we were able to actually get an efficient algorithm for actually solving these equations. So what we can do is we can sort of think about equations in terms of a matrix equation, AX equals B. Okay, so the A sort of encodes the coefficients of the m equations and n unknowns, and the B sort of corresponds to the result that you get for each of the equations. And once we do this, we put it in a matrix form like this, and we perform row operations via Gaussian elimination, and we transform this into something which is in upper echelon form, and we get some other B prime over here. And once we actually have it in upper echelon form, then we back substitute to solve. So then use back substitution to solve. Okay. All right, so let me give you an example of how we did this. We've done lots of examples, but let's go through one now. So I have x1 minus 2x2 minus x3 plus 3x4 equals 0, and minus 2x1 plus 4x2 plus 5x3 minus 5x4 equals 3, and let's say 3x1 minus 6x2 minus 6x3 plus 8x4 equals 2. All right, so this is the system of equations. It's 3 equations and, of course, 4 unknowns. All right, now we can transform this into the matrix equations by sort of doing the following. So we just said this, we have 1 minus 2 minus 1, 3, 0. So that corresponds to the first equation. Minus 2, 4, 5, minus 5, 3. That corresponds to the second equation. And then we have like 3 minus 6 minus 6, 8, and 2. Okay, run around with that? Yeah. All right, so now in order to solve this, we look at where the pivots are. So the first pivot is up here. We're going to use that to knock out the sort of stuff below it in the first column. So I'm going to use this to knock out the 2 down there. So 1 minus 2, 1, 3, 0. So what do we get? We get 0. We get another 0. And we get 3. And we get minus 1. And we get another.
Drop the negative on the 1, Professor.
Let's see.
On the first row.
Plus 1. Thank you. Okay, good. All right, so now what we do is we multiply by a minus 3 over here. Good. And then we added row 1 and row 3 together and put the result in here. So we get a 0 here. Looks like we get another 0. And then what do I get? I get 6 minus 6 plus 3. That's a minus 3. And I get 8 minus 9. That's a minus 1. And then I get 2 down here like this. All right. Yeah, that's right. Okay, good. So now let's continue on.
I think what he meant is when you copied the first row onto the next one, you forgot to include the negative sign.
Sorry, which one are you talking about?
So
First row.
yeah, it's
third
1,
column.
-2,
Oh,
-1. You forgot to include the negative 1.
Okay, put the minus 1. Okay. All right, good. Now, now we'll just knock the last row out by doing this. So we go 1, ooh, thanks. Minus 2, minus 1, 3, 0. I did it right this time, right? 0, 0, 3, 1, 3, and we get 0, 0, 0, 0, and then what? 5, right? All right. So what can we conclude? Not consistent, right? Because here's x4 over here, and we have 0 times x4 is equal to 5. So there's no x4s that satisfy that. So this is not consistent. I.e., there's no solution. Okay. All right. Now, what about the homogeneous system? So how about the homogeneous system? AX equals 0. Okay. Now, we've already done the work in terms of row reducing. So when I have A0 here, you know, by Gaussian elimination, it really goes to U of 0, right? The zeros don't, I mean, when you add things in the 0 column over there, it doesn't do anything. Right? So I can just use this matrix up here to look at the homogeneous system. So 1, -2, -1, 3, with the 0 here, 0, 0, 3, 1, 0, 0, 0, 0, 0, and another 0. Okay, everybody all right with that? Okay. All right, so does the homogeneous system have solutions?
Yes, it has solutions.
Okay, so definitely it always has a solution because the 0 is a solution. Okay.
Right.
Does this one have infinitely many solutions, or is 0 the only solution?
Infinitely many.
Infinitely.
Infinitely.
That's why.
We have 2 free variables.
Okay, you got 2 free variables. So remember, the free variables lie where you don't have the pivots, right? So I have x2 here, and I have x4, and those will be the free variables. So let x4 equal to t, which is free, and x2, let's say, being equal to s, and this is also a free variable. Okay. And now with the free variables, you just want to back substitute. So we have 3x3 plus x4 to be 0. That means that it's 3x3 plus t is 0. So that means that 3x3 is equal to minus t. So x3 is equal to minus t over 3. Okay, so we've solved for the free variable in terms of x3. All right. Now we just have to go back up to the top equation. So x1 minus 2x2 minus x3 plus 3x4 is equal to 0. Okay. So x1, so minus 2s, and then plus t over 3 plus 3t is 0. Okay? So that means that x1 minus 2s plus, okay, so that's 9/3, so I got 10/3 t is 0. Right? So x1 is equal to 2s minus 10/3 t. Okay? Everybody all right with that? And then finally, the solution you write out is x1, x2, x3, and x4. And then you just put everything in. So it's 2s minus 10t. Let's see what x2 is. x2 is s. x3 is minus t over 3. x4 is t. And now let's separate things out. So it's s. So with the s variable, it's 2, 1, 0, 0. Okay. And with the t variable, what do we get? Anyone?
Negative 10.
Negative 10/3. What's the next one? 0, right?
0.
What's next?
Negative 1/3.
Good. And then after that,
1.
okay, good. All right. And then s and t are allowed to be any real number. Okay, any questions on how we solve those? All right, so, I mean, you can almost guess that there will probably be a systems of equations problem on it. Good. Let me just say, I'm an instructor who will actually tell you what's going to be on the test. I'm not trying to hide anything at all. Okay? I want to make the expectations rather clear and sort of give you an indication that the stuff that you've been doing in your homework will hopefully help you on the exam. Great. Now let me just review. A concept that we talked about before. So this is a general system of equations. And so we have a general system of equations, AX equals B over here. And the solutions are X equals XP plus XH, where XP is a particular solution. So you just need one of AX equals B. And then XH is all the homogeneous solutions. Okay, so when you do this Gaussian elimination, you actually see that. So if I had a solution for the general equation, or just the equation that I had first, I would have a particular solution, and then I would tack on the homogeneous solutions to that. Okay, questions on this? All right, let's move on to the next topic. So let's see, I put 2 over here. So let me call this 3. All right, so now I want to talk about the idea of linear independence. All right, so here's a picture that one should think about. So here's a plane, let's say. And if I have 2 vectors in the plane here, v1 and v2, these vectors are linearly independent. And if I add one more vector inside of here, let's call this v3, these are not linearly independent. And one reason is that one vector can be written as a linear combination of the other 2. All right, so let me go over the definition. So definition. Okay. A set of vectors, I'll call them v1, v2, up to vt. And let's say they're in Rn. Okay, so they're n tuples. Is linearly independent. If and only if given C1 V1 plus C2 V2 plus CT VT in the 0 vector. So if I have an expression, if I write the 0 vector as a linear combination of the other vectors, then all the C's have to be 0. Okay, so in other words, the only way to write the zero vector is a linear combination of things in the set is if I just have the zero vector itself. Okay. So, if the set V1 to Vt is not linearly independent, then the set is called linearly dependent. And one thing that we proved is that if you have a linearly dependent set, then some vector can be written as a linear combination of the others. So that's one point. So if V1 to Vt is linearly dependent, then some Vj is a linear combination of the other vectors. Okay, any questions on this? Now, how do you actually show whether vectors are linearly independent or not? Well, so I want to focus on this condition star up here. So what we can do is we can sort of make condition star in terms of a system of equations setup. So, so star is equivalent to considering the following: AC equals 0, where I put the vectors V1, V2, up to Vt down the columns of the matrix. So I'm looking at the homogeneous system of equations. And once I actually set it up this way, all I need to do is show that this homogeneous system has only the trivial solution, namely the zero solution. So once I do that, then I could say that the vectors are linearly independent. So using the setup V1, V2, Vt are linearly independent if and only if AC equals 0 has only the trivial solution. Okay, any questions on this idea? So we can convert linear independence in terms of a system of equations. We know how to solve systems of equations using Gaussian elimination. And so once you kind of set the problem up in a certain way, you can actually solve it. So let me give you an example to do at home. Okay, so this is an exercise. Determine if the set of vectors, let's see, 0, 1, 5, let's see, 1, 2, 8, and 4, 1, 0, 4, minus 1, 0. Oh, it doesn't matter. Are linearly independent or linearly independent. Okay. All right, so, I encourage you to go home and or maybe you're home already, you can actually work on doing this problem. Okay, questions up until this point? Yeah, go ahead.
Early, the vectors that you drew out, the linear dependent, it's kind of a combination, like scroll or.
Yeah. Sure.
So linear combination.
Yeah. Sorry, which one? Oh, here.
Sorry, yeah.
Yeah.
So if it's linear independent, so if it's linear dependent,
Yeah.
it has that combination.
Yeah, so like V3, it's going to be in the span of V1 and V2. So V3 is a linear combination of V1. Okay, so these vectors are not linear. Good. So another way to think about linear independence is you sort of want the smallest set, which is not redundant. So what you can do is, you can sort of throw out one of the vectors and still get the same spanning set. Okay. So as long as you can throw a vector out, or you can throw a vector out and still get the same spanning set, it's not linearly independent. Okay. All right, other questions? All right, so now I want to go over the idea of spanning. I think this will conclude the review for the day. All right. So first of all, let's talk about linear combinations. So let V1, V2, up to Vt be a set of vectors inside of all that. Okay, so a linear combination of V1, V2, up to Vt is a vector W equal to C1 V1 plus C2 V2 plus CT VT, where the CJs are just real numbers. Okay, so if I get a linear combination, you just take combinations of vectors V1 up to V. Okay, so you can take a scalar times V1 and plus a scalar times V2 plus blah, 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 scalar times V2. Okay, those are all the linear combinations. So if I take two vectors like this, V1 here, and let's say V2, then all linear combinations sort of form a plane. Right? Okay. So that's it. You sort of want to generate a certain subspace by just looking at what combinations you can get. All right, so this is actually called the span. So the set of all linear combinations of V1 up to Vt is called the span. Okay, so I'll just write that out. So span of V1 up to Vt. So this is the set of all linear combinations. C1 V1 plus CT Vt, where the CJs are real numbers. Okay. All right, so in the picture, the span is just plain. All right. So so B is in the span of the vectors if and only if B is a linear combination of B1 up to B2. Okay, so something is in the span if and only if that's true. Now, let's again write this out. So if I take C1 V1 plus C2 V2 plus CT VT being equal to B. Okay. So what I can do is I can express this as AC equals B. Okay, where A is just the vectors written down the columns of the matrix. Right? So to see whether B is in the span of the vectors, we can again set up a system of equations. So B is in the span of V1 up to VT if and only if what happens? AC equals B has a solution, period. Okay. All right, so we can check whether something is in the span of vectors by putting the vectors down the columns of a matrix A and just using systems of equations. So again, it reduces to a system of equations problem. Okay, any questions on this? We've done lots of examples of this.
I just have a quick, maybe question or observation.
Yeah.
So span could be either a line, a plane, 3D space, and
Yeah.
if you go into the fourth dimension, fifth dimension, that's kind of what span is really saying. And if B lies in that kind of dimension, then it has a solution.
That's right. That's exactly right. So basically, you're looking at these geometric objects that you're talking about, a line, a plane, 3 space, 4 space, 5 space, and you look at what those vectors generate, and you just want to know whether B lies in that object or not. Okay.
Is this also just saying like B is a part of the range, or
Yeah.
there is, essentially there is a solution to this function?
That's right. So if you take A and you think of it as a linear transformation from Rn to Rm, right? And so the image is just going to be this span. So the image of A is equal to the span of these vectors. Right? And so basically you're just saying, it's exactly what you're saying, that you want to just see it whether B is in the image of this linear transformation.
Gotcha.
Okay. We'll connect that on Monday. All right. I didn't want to throw all this stuff at you today. Okay, so so on Monday, before I open up the Q&A, so Monday, the plan is to go over applications. Okay, so we're going to go over the balancing chemical equations and maybe some other applications too, and then we'll talk about linear transformations on Monday. Okay, so those will be the topics for Monday's review. All right, so in the remaining time, let me open it up to any sort of questions you have on the material, or any sort of questions you have about the midterm. No one asked how many problems are going to be on the midterm.
Well, do you have any sample exams to give us?
Not really. So the idea is that let me just tell you how many problems will be on the exam. So there'll be 5 problems that'll be worth 20 points each. The problems are going to be basically based on homework type problems. You know, you probably should be able to solve a system of equations. Probably you should be able to determine whether vectors are linearly independent or not. You know, you should be able to see whether vectors in the span. I'm sort of giving you all the hints right now. So. And I'm trying to have you focus your studying too in terms of what type of things that the midterm will emphasize. So I've actually given you a sample problem already, right? Like this example up here. Okay. All right, other questions?
Yeah, I actually have one, but it's related to linear transformation. Should I wait until Monday or should I ask now?
We could try to address it now, but why don't we wait till Monday?
Okay, that's fine.
Okay, thanks.
Thanks.
Other questions? I'm
Yeah,
happy.
well, I had one. Will any of them be like super proof based, kind of like some of the like homework questions we had where we're just proving something?
If it is, we'll just have to use the definitions.
Okay.
Okay. And that's why I want you to know the definitions very well. So, you know, if you want to show like vectors are linearly independent, you look at the linear combination being 0, and then you want to show the coefficients of 0.
Okay, so it's not going to be something where we would have to address like some of the theorems in the textbook to just prove our answer?
No, I would make it fairly basic in terms of any sort of verification would be pretty close to the definition.
Okay.
I have a question regarding the applications and the use of a calculator, especially for like chemical equations.
Yes.
So, in a TI-84 calculator, there's a function where it's a reduced row echelon form.
Yes.
And some of these chemical equations require many row reductions just to get it into an upper echelon form. So are we allowed to use that function on a TI-84?
But that's a good question. So I would say that the problems that I would give you in terms of balanced chemical equations, they can be done by hand. All right. And
Okay.
you know, you can check your work. I'm okay with that. But basically, you have to show your work on the exam.
Okay. Yes, because there was one where there was like 6 or 7 different elements. So like the row reduction was getting very tedious,
Right.
and I just reduced row echelon formed it with a calculator, just to kind of check my work, I guess.
I'm happy if you check your work, but the work has to be shown on the exam.
Of course.
Okay.
Thank you.
And the thing is, I actually, on every exam, I actually write out solutions, you know, for myself beforehand, and make sure that the calculation is something that really all I can. Okay. So I'm trying to make sure that I'm mindful of your time. I know I'm trying to give you the maximum amount of time in terms of 60 minutes on the exam.
Okay, appreciate it. Thank you.
Okay. Other questions? Yes, no?
I just have one quick thing. Are we going to be expected to regurgitate definitions like what you just wrote for span?
I said that you are accountable for definitions. I could ask you to define what it means for linear vectors to be linearly independent, for example. So you're accountable. I actually wrote the definitions you're accountable for at the beginning of the review, right? But I'm not saying that you have to remember all the definitions. I gave you the ones that you're accountable for. Like we're here. Okay? Did that answer your question?
Not really, but it's fine.
Wait, so I mean, it's, these are definitions, they're in the book, I've written them down, you know, in class, you have to know. I wrote four of them, the four down that you need to know. Okay?
I have another question regarding span.
Yes.
So if you only have two vectors,
Uh-huh.
that span is guaranteed a plane, correct?
Well, if the vectors lie on the same line, you just get a line.
Oh, yes, if that was not the case, they'll give you a plane.
Then you get a line.
Okay, all right. I just kind of solved my own question. Thank you.
Okay, good. I'm glad. Oh, coming back to the definitions, I hope those are easy problems. I mean, I'm trying to give you some problems that, you know, if you know, you memorize the definition, then, you know, you get points on the exam, so. Okay, other questions? All right, did you want to, I think Sydney, did you want to ask your question about linear transformations?
Sure. It's pretty short too. It was just from the homework that we just turned in from 1.9.
Okay.
It was finding the standard matrix of T, the one that performed a horizontal shear that transforms E2 into E2 minus 2E1 and then reflects points through the line x2 equals negative x1. So when I did that, I kept, to find a standard matrix, I was using the horizontal shear, like standard matrix, if you will, and then the reflected one. But when I couldn't get it right because I needed to flip them and I wasn't sure why. Like I needed to multiply the reflected one. I'm sure you know what I'm saying, but I couldn't figure out why they needed to be in that order.
Because the thing is, what you're doing is, so let me just write it this way.
Okay.
So let's say A is the matrix with the shear. Okay. So you're applying the shear first. Okay.
Right. Right.
And the A prime is, let's say, the flip. So you apply the A prime after that.
Right.
So that's the order it should be in.
Okay. Okay. Okay.
Does that make sense?
Yeah.
Because you're applying this one, it's a composition of functions. So
Right.
you're applying this to X first, and then you're applying A prime after that.
Okay. Okay. Thank you. That makes sense. Mm-hmm.
Okay.
Thank you.
We can actually go over that problem if we have some time on Monday if you want. Okay, great. Yeah, okay. I'll give you a little. Okay, Monday. Yeah, okay. All right. Other questions? Okay, good. So we will again meet on Monday, and I will lecture for a bit, and then we'll open up for some Q&A. Okay, so have a good weekend.
Thank you, Professor.
Thank you.
Thank you.